Greetings, my math Padawans. This is lesson 410, graphing polynomials. The equations that we've been talking about over the last couple weeks, especially with all that factoring we've been doing, are called polynomial equations. And the word poly, or the prefix poly, means many, as perhaps you know already. And a polynomial is defined as a monomial or the sum of monomials. Now, I have here the general form. Don't be freaked out by that form. That's just like the standard way that you'll see in any math textbook when it talks about defining a polynomial for what it is. But there's a couple things that are important about writing polynomials. We always start with the highest exponent. So that n would represent the highest exponent. We call that the degree. And then the number that's in front, the starting number, is what we call the leading coefficient. And then the number that's all the way out here on the end is called the constant. Okay, I'll give you some examples on the next screen that you'll see. But it's really important that a polynomial is written in standard form, that we always go from the highest exponent to the lowest exponent. The other thing that's important, another characteristic, is all the coefficients have to be real numbers. So as far as the numbers that's in front of the x values, all of those are going to be reals. And all of the exponents have to be positive integers. As I said, I want to give you some examples because looking at this form it just can get really confusing. So let's look at a couple examples and also talk about classifying polynomial. So everything that's here in the far right column are examples of polynomials, and they're different ones. So like again, you'll see my crazy form written here in the middle. That's not really all that important. But if we look at it, like for example, we've looked at quadratic equations before. So this third line down, a quadratic equation is a very specific type of polynomial and is classified based upon its degree, which is 2. So a quadratic equation has a degree of 2. If we go a step down, an exponent of 1, like we see in this equation right here, we call those linear. And if there isn't an exponent, okay, technically there is, but we don't write it, right? So x to the first, because we would never write x to the first. This guy right here is actually technically x to the 0 power. But since x to the 0 power is equal to 1, that actually never shows up. But this is called a constant. If we go 1 degree bigger than a quadratic, a degree of 3, see the highest exponent of 3, we call that a cubic function. And if you see a degree of 4, that is called a quartic function. Anything bigger than that, we typically just say it has a degree of, like, say, 5 or a degree of 7. We usually classify that by just saying the degree number. Okay, let's take a look at a couple problems and see if we can tell whether these are polynomials or not. So let's look at A. So, are all of the exponents positive integers? Yes, they are. This has an exponent of 5, that's 2. There is an exponent technically of 0 here. So all of the exponents are positive integers. And then we look at the coefficients. Are they all real numbers? And again, the only thing we're looking for is an imaginary solution or an imaginary number. And that's what I do not see here. I see a -4, I see a 7, and a -2. So A is a polynomial. So is a polynomial. And because it's a polynomial, we can identify the degree. Again, remember, the degree is the highest exponent, which is right there. It's a 5. And the leading coefficient is the number that's right here in front of it, which is -4. Okay, let's go on and look at B. Is B a polynomial? Well, this square root of 3 looks kind of weird, but it's a real number, so that's actually not a problem. And all the exponents are just fine. The difference that you will notice with this problem is it's not written in standard form. So that's something that we kind of like to do first. We kind of like to take and write that in standard form. So what we can do is we can rearrange some things. So I can put that square root of 3, x to the 4th first, and then I can put the plus 0.5 x squared next. So that will allow me to identify the degree pretty easily, which is the highest exponent of 4, and then the leading coefficient, which is the number that's in front, as being the square root of 3. So it is a polynomial. What about C? Well, let me look at C. Okay, that's fine, but look here. Negative in the exponent. That's no good. So this is not a polynomial. Okay, what about the next one? P of x. Oh, look here. That's weird. That's weird. That's not allowed. So that is not a polynomial. No variables in the exponent. All my exponents have to be real. All my exponents have to be integer values. Okay, now we know what a polynomial is. Let's try to see what a graph of a polynomial can look like. So the first thing we're going to do is we're going to create a table of values for this equation. So a table of values we're going to do just like we've been doing before. Nothing new, nothing different. We'll set up some numbers. We'll put some numbers down here. I'm going to go from -3 to +3. And for each one of those, what I can do is I'm going to take them and I'm going to plug it into the equation. So I'll take that -3 and I'll plug it into the equation. And I'll do -3 to the third minus 3 times -3 plus 2. Now, I'll bust out the calculator, of course. But that's -27 plus 9 plus 2. And when I do the math, I get -16 for my y value. It's basically repeat this for each one of the following values or each of the next values. So I'll do the same thing with -2. Plug it into my equation. That'll give me -8 plus 6 plus 2. That equals 0. And I continue through that. So why don't you pause the video right now? Make sure you can plug a couple of these into the calculator. And then on the next screen, what I'm going to do is I'll have my table of values filled out. And I'm going to go ahead and plot those coordinate pairs as well. So we can talk about what this graph would look like. Again, so pause the video, finish this table of values that you see over here on the left side of the screen, and then we'll continue from here. Okay, so here is your completed table of values with all the numbers. And again, I just plugged each one of those into my equation and calculated the y value. And then I've taken those values and I've plotted the points over here. Now you'll notice my graph does not include the point -3, -16. That won't fit on my graph. And 320 is also not on my graph. But I did the rest of them right here. It's really hard to tell what this graph looks like. So we might need just a little bit more help with this. We might need to figure out and maybe use a graphing calculator or a Desmos to help us figure out what this thing looks like. But if we plug this into Desmos, we'll see the lines and the points connected in this way. So you get a graph that looks like this. You'll see that there's some changes in direction, right? This graph will go up, it'll change direction and go down, and then it'll go back up again. So there's some different characteristics that polynomials have that our other graphs haven't. One of the things you'll notice is there's not a parent function for these. All of these polynomial equations will end up looking slightly different than the others. So there's not like one big rule or one big parent function that we're going to move around the graph. Instead, we're going to have to rely on a graphing utility to help us out, or maybe some other rules that we'll come across along the way that'll help me figure out what the graph of these polynomials look like. But let's take a moment to identify some of the characteristics of this equation. So before we continue, I want to make a note. A lot of the things that we'll use here, some things will be listed as coordinate pairs, some things will be listed in interval notation. And interval notation, when we're talking about polynomials, is a lot easier to use, as I'll point out. But just to remind you of interval notation, this first inequality, if you would list that and write that as an inequality, we would write it x is greater than or equal to -3, right? That's -3 on the number line. So it would be x greater than or equal to -3. If we write this in interval notation, I want you to notice something. First of all, a closed circle will be a bracket. And then we know we keep going forever in that direction. So it's like we start at -3, and where do we end? We end at infinity because it keeps going forever. So in interval notation, that number line that I have there for the first one would be x greater than or equal to -3 would look like this. It would be bracket, -3, comma, infinity, and then a parenthesis. For my second problem, right, that's at 6. So to write that, that would be x less than 6. And again, when we do interval notation, it's a parenthesis. So if I kind of think about this, I kind of think about where do I start all the way over here to the left? Well, that's at -infinity, right? That's the furthest to the left I can go. And where does it end? It ends at 6 with a parenthesis because it can't equal 6. That's the difference between the closed dot in the first problem and this open circle in the second. And then when we get to this last one, this is everything. This is what we call all real numbers, right? You've seen me use that symbol before. In interval notation, again, think about where I'm starting. I'm starting to the far left. That's at negative infinity. Where am I ending? I'm ending at positive infinity. So I would be able to write interval notation, negative infinity to comma, positive infinity for all real numbers. That's just a quick reminder of interval notation. Please make sure you ask questions if this is something that doesn't make sense to you. But I'm going to absolutely use it when we go to this and we start talking about the different characteristics of a polynomial equation. So try to get it as we go along. I'm going to go right down my list over here on the right-hand side of the screen, and I'm going to identify things based upon what's there. So first things first, let's talk about classification. And again, remember, we're looking at the degree of this problem. That has a degree of 3. So we would call this a cubic equation or a cubic polynomial. Okay, what about the domain? Well, if I look at that, there are no breaks in my graph. So the domain of this equation is all real numbers. And instead of me writing out, remember, all real numbers is fine, but instead, I'm going to use my interval notation and say from negative infinity to positive infinity. Okay, good. It doesn't end to the left, it doesn't end to the right. These two ends keep going on and on. And the range, the same thing. This graph goes up forever, it goes down forever, so we got the same thing going on for the range. The range is all real numbers. Or again, I'll write it from negative infinity to positive infinity. Okay, maximums. Okay, maximums are going to be coordinate pairs. Okay, so we need to look at this graph and figure out, where does my graph have a maximum? Where's there a highest point? Right there's a highest point, right? This point right here ends up being the highest point on the graph. Now, it's not the highest forever. I understand that. But it is a maximum point. So we're going to write that in there as a coordinate pair, negative 1, 4. And then what about a min? Does this graph have a min? Yes, it does, right here. That point right there is, in fact, a minimum. So we will list it, 1, 0. Polynomial equations can have multiple maxes, multiple mins. We'd write them all. We'd write every single time that graph went from, look here, this graph goes from going up to going down. That creates a maximum. This graph went from going down to going up. That creates a minimum. What about an x-intercept? Where does this graph cross the x-axis? There's a point right there that crosses the x-axis, and right there that crosses the x-axis there as well. So we'll list both of them. Negative 2, 0, and 1, 0. Notice these are coordinate pairs. What about the y-intercept? Well, the y-axis is right, it goes up and down. So that point right there crosses the y-axis. That's the point 0, 2. So far, those things you should be okay with. You should have been able to do those without any issue. Those are just looking at the graph and identifying them. Here's the new stuff. Increasing and decreasing. So what I want to do is I want to look and I want to start with my pencil here on the left side of the graph, and I want to trace it from left to right like I read the book, like I read a book, from left to right. You'll see me tracing the graph from left to right. So what I want to do, I want to think about, as I trace this, when am I moving my pencil up? When am I moving my pencil down? Those are going to be what indicates when I'm increasing and when I'm decreasing. As you'll notice in this graph increases, and then it decreases, and then it increases again. So we're going to write those intervals, and we're going to use interval notation. So we're going to say, where does my graph start increasing? Well, my graph starts increasing to the far left, negative infinity. And where does it stop increasing? Now, this is the part you got to really pay attention to. We always use x values. So what is the x value where this graph stops increasing? Well, if I go all the way down here and look, it's at the x value of negative 1. Now, just be careful because I'm not numbering by ones across my x-axis. Each one of those blocks is worth 0.5. So let's keep going. When and after I go at from negative 1, then starting at negative 1, my graph decreases till I get to this x value, which is a x value of positive 1. So again, I go, where do I start decreasing? I decrease from negative 1 to positive 1. And then starting at positive 1, my graph goes up again. So my graph is increasing again from 1 to infinity. That's really important. So just think about tracing your graph, tracing the line. It goes from increasing to decreasing to increasing again. Okay, now let's talk about this other part. Where is my graph positive versus where is it negative? When I'm talking about this, positive is when is it above the x-axis. So that's where all my positive y values are. And where is it negative? Where is it below the x-axis? And again, we're going to use x values to determine that. So if I think about this, my curve is below the x-axis right here. From where to where? So if I write that out in interval notation, from negative infinity to the x value of negative 2, my graph is below the x-axis. And then starting at negative 2 till, well, when? Well, the rest of the graph up here is above the x-axis. So starting at the x value of negative 2 till forever, it's positive. So positive and negative is above and below the x-axis. Okay, one more thing to talk about. End behavior. And end behavior is simply exactly that. What happens on the ends of my function? So for that, I'm looking at the two arrows that are here and the other arrow that's down here. So I'm just going to draw those two arrows the way they are. If I look on the left side, my graph is pointing down. And if I look on the right side, my graph is pointing up. I'm not going to go into all of the details with this at this point in time, but the degree and the leading coefficient tell me exactly what's happening with end behavior. So this chart's going to tell you. Now, I don't want you to pay too much attention to that crazy notation, but just know if the degree is odd and the leading coefficient is positive, then my left side points down and my right side will point up. If my degree is odd, but my leading coefficient is negative, then the left side will point up and the right side will point down. If I have a degree that's even and the leading coefficient is positive, both the right side and the left side point up. And if my degree is even and my leading coefficient is negative, both of my ends point down. So for example, if I'm looking at this equation right here, this is in fact a polynomial. You'll see that my degree is equal to 4 and my leading coefficient is negative 0.3. Well, that is even, and this is negative. So that means both of my ends will point down. So my graph will look a little, at least on the ends, my graph will point down on both sides. It's helpful to know this, especially when we get into actually graphing these on our own. Okay, so one problem here I'd like you to try. So there's a lot going on with this. So pause the video. And then what I want you to do is I'd like you to fill in the table of values here. I'd like you then to jump on your computer and I'd like you to, in Desmos, actually type this equation in Desmos. Okay, to get to the exponent, to type in an exponent, you do shift and then the number 6, the little caret that's there. Type that equation into Desmos and then it will give you your graph and what your graph looks like here. And then I'd like you to classify. Go through all of these different parts and identify the characteristics of the polynomial you're going to come up with. Do it in that order, please, and then I will, of course, go over the answers with you here momentarily. Pause the video, do some work. Talk soon. Okay, here is your table of values. You can see it all right there. There's your table of values. Here's the graph that Desmos told us about. Notice my tracing, right? Goes down, goes up, goes down, goes up again. And here we're going to classify all of these different parts. So classification first. First of all, I noticed that my degree is 4. So this is in fact a quartic equation. 4, degree of 4, like a quarter, 4. The domain, all real numbers. And again, if you're going to write that in interval notation, you'd write it like that, all real numbers. Folks, polynomials will typically have a domain of all real numbers. Again, when it's not, we'll know. The range, now this is a little bit different. Look here, there is definitely a smallest spot. It's like all of my values are going to be greater than or equal to -9. If you are going to write that in interval notation, it would be -9 to infinity. So -9 is the lowest value, and it goes up from there. Maxes and mins. Let me look at those max values. There is a max right there. That's it. And what coordinate pair is that? That's the coordinate pair 1, -8. What about mins? There are two of them. There's one right there, and there's one right there. That point is at the point 0, -9. The other is at 2, -9. We can look at the table of values. We can see that. We plotted those points, of course. X-intercepts. Where does this graph cross the x-axis? Right there and right there. That is at the point -1, 0 and the point 3, 0. What about the y-intercept? The y-intercept is right there. That is at the coordinate pair 0, -9. Okay. Increasing and decreasing. So if you look at this function decreases, then it increases, then it decreases again, then it increases again. Okay, so where are we decreasing? We're decreasing. My graph starts from decreasing, so I'm decreasing from -infinity to, again, the x value of 0. Then I'm increasing starting at 0 till I get to the x value of 1. Then I'm decreasing again from 1 to 2. And then I'm increasing from 2 to infinity. Okay, where is this graph positive? It's positive above the x-axis. So when is this graph above the x-axis? Let's see here. That's from -infinity to -1. And then from 3 to infinity. Because if we look at it between -1 and 3, my graph is below the x-axis. The end behavior. Both ends point up. And I knew that because my degree was even and my leading coefficient was positive. I know this is a lot. We're absolutely going to have to practice it, and I will be with you the entire way as you go through this, some more example problems. So I'll see you in class, and we will absolutely practice this more. Don't worry, I have you back. Talk to you soon.